Maximum depth of a binary tree. Given the root of a binary tree, return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. So for this particular problem, I'm actually going to take a little bit of a different tact. I did not do a practice run, so hopefully this goes smoothly. This looks pretty simple. So we need to find the longest path. So in this case, it'd be 3. So 1 including the root, 2, and then 3. So it's 3 levels deep, including the root level. All right, let's think about theoretical limits. No matter what, we are going to have to traverse the entire tree because we're not really going to know. We have no way to guess whether to go left or right when looking for this maximum depth. All we need to know is we need to go as deep as we can. And then however far deep we go, that's what we ultimately return at the end. So given that we do have to traverse the entire tree, that gives us a few options. First of all, that puts our minimum runtime at O of n. And in fact, that's pretty much what's going to be, because at every step, we're really just going to do a check on have we gone deeper than we've gone before? Yes, no. So that's a constant time comparison. So we're going to traverse the entire tree. So that's O of n things, steps, and at each of those, we're going to compare our depth, which is a constant time. That puts our runtime at linear. And it's a tree, not a graph. So the number of edges is always going to be pretty similar to the number of nodes. So it's O of n, it's not like edges and nodes. It's just one or the other. They're about the same. And since we have to traverse the entire tree in linear time, we can use either depth first search or breadth first search. Those are pretty much the same. If we have, assuming we have no idea where that maximum depth is, then there's really no difference between the two. If we had some idea, maybe we could go for a depth first search and then kind of do a heuristic to search that way first, and maybe gain back some real world runtime, even if it doesn't reduce the theoretical limit. But assuming we have absolutely no idea, what I'm actually going to do, I think, is go with breadth first search, partly because it's a little more conceptually straightforward, in my opinion. Because with breadth first search, you can go level by level. You can go level 1, level 2, level 3, and then you don't have to. So if you did depth first search, for example, you could go at various different levels. So you have to keep some like global variable and like compare that, or like return the maximum of what you received from a child recursive call versus what your current level is, something like that. It's a little more finicky. Not that either one's particularly hard, but I think breadth first search is the way to go, and then that gives you a chance to point out like a little more elegant way of doing it. All right, so let's go ahead and get started. So we need a queue. It's gonna be a double-ended queue. So in C++, that's in the DQ header, I think. Yeah, double. So you can add or subtract from both ends. You need that for your breadth first search. And then we're gonna go ahead and make our queue. So DQ, DQ, and it's gonna have pointers in it. So tree node pointers. And I'm just gonna call it queue. And we're gonna put the first thing on it. So queue dot push, I don't know, back, I guess. Back. Not that it matters because there's only one item, but we're gonna push the root on. And then in classic breadth first search, we're gonna go while not empty. First, we would get the first thing off of it. So I'm gonna go ahead and declare just like a temporary thing. So I'm not like constantly declaring inside the loop. So tree node, pointer node equals queue.front. and then q.pop front. Actually, let's see. So okay, we need our. I'm gonna make a return value. I need to track that. So ret. Wait. Okay. Before I forget, our input is a pointer. That should mean you should check if it's null. If you have a pointer input, check if it's null. It's an edge case. It's a common edge case. Pretty much every interview question is going to have, if they have input pointers, they're going to want you to ask about that as a potential edge case. So if not root, return 0, depth of 0. Otherwise, oops, what did I do? Go back. All right, so assuming our root is not null, we have a depth of at least 1. And then at the end, we're going to return that, of course. All right, so what we're going to do is the way you do level order traversal in breadth first search is you use a for loop. Meaning, all right, so for, I guess, yeah, so for the length of, so int. All right, so int, it doesn't super matter. I'm gonna say int, I don't know, n, I don't know, n equals the size of the queue. So queue.size, and then n is greater than 0. All right, what this is doing is the size of the next frontier of our breadth first search is whenever we get to, whenever we start this for loop, however many items are in the queue, that is our entire next frontier. We haven't had a chance to add any remaining children, and ideally we wouldn't get to the start of this for loop until we've finished off the prior frontier. So what that means is we're going to continuously pop things off of the queue there, actually. So node there. That would make sense. While the queue is not empty, the size of our frontier. Okay, there's our node. And then we're going to, at the start of the for loop, actually, let's say return is, I'm going to, sorry, I'm jumping around. I'm going to start this off as 0 here, this return value, so it's a size of 0. But before getting to the for loop, I'm going to increment it, so ret. So when we start off with the root node and we get to the start of this for loop, then it's a size of, that's the first depth. And then, we'll add its children to the queue. And then, yeah, so this is what our actual constant time work is at each level. And then here, all we're doing is adding children to the queue. So queue dot push front, sorry, push back to the back of the queue. So node left, and then I guess the right child, push back. Okay, let me think. We need to check for null children at some point. So that's either before we add it or after we add it, and then it's like not there. So what that means is, from like a logical reasoning perspective, I think it's usually easier to do it after popping it off the queue. So if not node, continue. So if the node at the front of the queue is null, so I'm going back and forth. It's conceptually easier to do this. You could keep the queue size a little bit smaller if you don't do that, and if you instead check here, I'm gonna do that. That would be a little bit better, actually. It's not like, I don't know. I'm on the fence. I'm really on the fence, but I have to pick one. Either way will work. So if not, node left. Wait, if node left. There we go. We're not gonna have the continue clause there. And then if node right, then we push the right child on. Okay, let's see. Yeah, I guess so. That would keep the queue size a little bit smaller. So I think that's it. At each level, all we're doing is adding the children. And then when we get to the end of the frontier and we've added all the next frontier's children, then we get to the start of the loop. And, okay. And then I think this might be everything. This is it. So I'm gonna step through this example here mentally. So first of all, write down the runtime. So O of n, time and space. We talked about why it's O of n time, and it's O of n space because of this this queue here. This queue could, suppose the input is just the root, then you're going to have the entire tree on your queue. So it's O of n. And realistically, okay, at each successive level, you potentially double the size of the next frontier. So that means, okay, suppose you have 4 items in this bottom level. That's 4 out of a total of 7 possible nodes. That's more than half. And at the next level, you'd have 8. 8 out of a potential 8 plus 7 is 15. 8 out of 15, that's more than half. So more than half your nodes at any given time could potentially be on the queue. That's within a constant factor of linear. So that's why you have linear space in your queue. Okay, so O of n time and space. And then now for the example. So our queue has, all right, I'm gonna write the queue there. All right, so our frontier, so we're at a depth of, so we check if the root is null. It is not null, so we don't do that. Return starts off as 0. Our return value, so return is 0. And then Q is that. Return is 0, Q, and then, okay, so we put the first node, so we put 3 onto our queue. And then we start off with our loop. All right, so while the queue is not empty, the queue is not empty. So return value, we're going to increment. And then we do a for loop. So we do one iteration. So all right, node pop front. That's this 3. So we're going to take that 3 off. And then 3 does have a left child and it does have a right child. So we're going to add both of those to the queue. So 9 and then 20. Next iteration of the loop, we increment our return value again. And then this time we're looking at okay, so first node is 9. Pop that off the queue, front of the queue. That has no children, so we don't add anything. Next iteration of the for loop, pop that off the queue, 20. 20 has a left child and a right child, so we're going to go ahead and add those, 15 and 7. Okay, that's the end of the for loop, so when we go to the top of the while loop, increment return value again, 3. And then we're going to pop 15 off the queue first, so 15. That has null children, so we're not going to add anything to the queue. Next iteration of the for loop, pop 7 off the queue. That has no children, so we're not going to add anything to the queue again. And then that's the end of the for loop, and then now our queue is empty, so then we break out of the while loop, and then we return 3. That is our expected return. So while I was stepping through that, I did realize actually, okay, in this last iteration, if we had added null children, we would need to somehow account for if the entire next frontier, so this row down here below the 15 and 17, we need to have to account for if that was entirely null. and then subtract 1. So that's like kind of a finicky case. So actually, for this problem, and I think in maybe in general for especially tree traversal, but this frontier wise, um, breadth first search, it is better to check before putting in things into the queue if the children are null, so that way you have an easier time knowing when to break out of the while loop entirely, because that's just when the queue is empty, and you don't have to account for when the queue is entirely of null values, which you know that's a pain. So just do it this way. Yeah, and then I think that'll do it. So let's go ahead and give it a run. Oh, I'm not signed in. Let me pause that and get back to you. All right, and we're back. Let's give it a run. Accepted. Nice, nice. I did not change anything before and after the pause, and let's go ahead and submit. Cool. Yeah, you see, last time I tried this was quite a while ago. And then mark it off, and we're done. Good night.